get this going. So today we have a smaller chapter, chapter 13. Chapter 13 now is on loci, sets of points. So what is a loci? It's a set of points satisfying some condition.
A loci.
Loci.
A loci.
Or sorry, loci is plural. Locus. Locus is a set of points satisfying some condition. Loci is the plural of that. And so when we talk about a geometric figure, some geometric figure, so if I say, here's some point, here's a circle, here's some point with radius, I don't know, say the radius is 3. One way I could describe this geometric figure, this circle, is it is the set of all points whose distance from this point is 3. It's a set of all points satisfying some condition.
That's loci?
That's a loci, or a locus. Loci is a plural of locus. So I could call this a set of all points whose distance from the origin is 3, or I could say it's the locus of points whose distance from the origin is 3. So he's just introducing this word to you because it's one that often comes up in higher level textbooks. So a locus of points is just a set of points satisfying some condition. That's it. So he spends some of this chapter going over some basic set theory, but I introduced all that basic set theory to you guys way back early in the course. Let's remind ourselves really quick of what sets are. What is a set?
A set?
Yeah, what's a set?
Points that follow specific.
Here's one set. This is a set 1, 2, 3.
Yeah.
There's a set. Here's another set. 1, 3, 3, 2. Question, are those two sets the same set?
Yes.
Yes.
Oh, yeah.
Remember, in sets, all that matters is everything in this set in here, and is everything in this set in here. Some high-level language we use to describe a set is we say that they are a unique, unordered collection. Unique, meaning duplicates don't matter. We only care if it shows up at least once. Unique and unordered, meaning order doesn't matter.
Yeah.
Right? Okay, and then some of the basic set notations. If I said A was equal to the set 1, 2, 3, and if I said B was equal to the set 3, 4, 5, two basic set operations that we talked about was union, A union B. What is A union B?
It's 1, 2, 3, 3, 4, 5.
It's 1, 2, 3, 3, 4, 5, or just 1, 2, 3, 4, 5. There's no point putting the 3 in there twice. It doesn't change anything.
Yeah.
It's everything that's in A or B. And then we had A intersect B.
Is it not 1, 3, 2, 4, or what?
What's A
Just
intersect
mixed
B?
together? They're mixed together?
No. Oh, I think you're thinking of a cross product. A intersect B is everything that's in A and B. Where do these two sets intersect?
At 3.
They only intersect at 3. When I had two geometric objects, I had this circle and I had this line. Where did they intersect? What points did they have in common? The point right here and the point right here. This line is an infinite set of points. This circle is an infinite set of points. They had 2 points in common, that point and that point.
Okay, yeah.
So I always tried to get you to think about geometric objects as sets of points. And we can do all the set operations that we know and love to these various sets. So I think you just give some descriptions to get you comfortable with the language. So the first description. The locus of points at a given distance R from a given point. The locus of points. So here's our given point. Let's read this again. I want the locus of points at a given distance R. So I want the locus of points at a given distance R from a given point. What are all the points a given distance R from a given point? Let's say O is my given point. What are all the points a distance r from O?
All the points.
It's just a circle. So that's one way to describe this circle. Let me read it one more time. Most of this is just getting comfortable with the language. The locus of points at a given distance r from a given distance, or from a given point. Let's do another one.
A
Go ahead.
radius would be a locus.
A locus is a set of points satisfying some condition. If I could say the set of points such that blah, 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 blah.
And R is the set of points satisfying.
Let's write out this
Radius,
circle more
right?
explicitly. Do you remember set builder notation?
If you explain it, I'll do it.
So let's look at this set. Let's look at the set of all x such that x is greater than 2 and x is an integer. So this is set builder notation. We give some dummy variable, what we call a dummy variable here, and then some condition over here. This is shorthand for writing out the set. I'm looking for everything that's greater than 2 and an integer. What's greater than 2 and an integer? 3. What else?
4.
5, 6, 7. Now this is an infinite set, obviously. I can't write all the elements, which is one of the reasons set builder notation is so handy. Gives us a concise way of talking about these infinite sets.
Okay.
So there's one example of set builder notation. Another one I could do is, let's look at the set of all p such that the distance from O to P is less than or is equal to R, where D here is some distance function. I want all the points whose distance from O is equal to R. That's a circle. Set of all points P satisfying this condition. You're probably not used to me just writing a distance function like that, so I might just say the set of all P where or such that distance, we can spell it out with words if we need to, distance from O to P is R. So,
Okay.
set of
Yeah,
all
I
points.
gotcha.
So there we go. So this is a locus. It's a set of points satisfying some condition. You should always be able to write your locus in the set builder notation. The set of all P satisfying some condition. Okay. So the next example he gives is the locus of points at a given distance D from a given line L. So I've got some line L here. And now I want all the points some given distance D away from this line. Let's pretend D is the length of this segment. So there's our distance. What are all the points a given distance D from this line?
That we can get out of that line.
I want you, if a point is this far away from this line, we want to include it. We don't want that point, because it's not that far from this line. We do want this point, because it is that far from this line. We want all the points whose distance is this far from this line.
It's just a
An
parallel line.
infinite amount.
Gives me this parallel line, right?
Yeah.
All the points there. Is that it?
No, other side.
Other side.
Other side.
And this parallel line.
And then you have one on both sides. You have
And then there you go. That would be all those points.
Well, yeah. Oh no, you're right.
Okay. All right. So that gets you comfortable with some of this notation, or some of this verbiage. Locus of points is just a set of points satisfying some condition. Now, we often have some geometric figure, and we want to know that two properties are true for that geometric figure. Well, maybe you should have said this first. You remember the subset symbol? What we mean when we say A is a subset of B? What do I mean when I say A is a subset of B? What do we mean by A is a subset of B? We mean everything that's in A is also in B.
But But everything in B is not in
No, we just mean everything that's in A is in B. That's it. That's the definition of subset.
A. Okay.
So in this case, is A a subset of B?
Yes.
Yes, because everything that's in A is in B. Question, is A a subset of A?
Yeah.
Yeah, everything that's in A is in A. Every set is a subset of itself.
Okay. Yeah.
Two ways that we can prove, or one way that we prove two sets are equal, is we show that A is a subset of B and B is a subset of A. If A is a subset of B and B is a subset of A, then they're the same set. Everything that's in here is in here, and everything that's in here is in here, then the two sets are equal.
Yeah, okay.
So this is a common strategy for showing that two sets are equal. Show they're subsets of each other. That's how you show two sets are equal, as a general rule. Very common. Okay, so what we're going to do is we're going to have some geometric object, some set of points, and we're going to show that two properties are true for that set of points. The way that we are going to do that is we're going to let A be the set of points that satisfy the one property, B be the set of points that satisfy the other property, and then show that they're the same set. They're the same geometric object. So the geometric object that has the one property also has the other property. Let's see that in action. So our first theorem. The locus of points P, equidistant from two given points A and B, is a set of points on the perpendicular bisector of the segment A and B. So let's get a picture for this and write this one out. So I've got 2 points A and B making a segment. You with me?
Yeah.
Alright, first thing I want you to do is look at the set of all points whose distance from A and B is the same. So we look at this point. That's the same far from A as it is from B. We look at this point. We look at this point. We look at this point. And we end up with all these points. Those are all the points whose distance from A and B is the same. You with me?
Yeah.
Now we're going to look at the perpendicular bisector of A and B. Different locus. Perpendicular bisector of A and B. That's this. We're proving that those two geometric objects are the same object.
You're saying
The set of all points equidistant from A and B is the perpendicular bisector of A and B. That's what we're proving.
okay.
So I'm going to let S1 or something come up with some set name. S1 be a set of all points whose distance from A and B is the same. I'm going to let S2 be the perpendicular bisector of AB. And then I'm going to prove that they're the same set. I'm going to show everything that's in the one set is in the other, and everything that's in the other is in the one. Therefore, the two sets are the same. Therefore, it's the same set of points. Therefore, it's the same geometric object. Make sense? That's the big picture how we're going to go at this. All right. So this is Theorem 13.1. So 1, let segment AB be given, comma, let S1 be the locus of points equal distance from A and B, comma, let S2 be its perpendicular bisector, comma, and let C be the midpoint of A and B. Just set up a picture really quick. So, of A and B. Alright, so we got all this set up and we got our point C here labeled. Now, what do I need to do? I need to show that if a point's equidistant from A and B, it's on the perpendicular bisector, and then I need to show if it's on the perpendicular bisector, it's equidistant from A and B.
Okay.
Alright, so which way should we go first? Should I start with a point that's equidistant, or should I start with a point that's on the perpendicular bisector?
Point is on the bisector.
Alright, so let P lie on the perpendicular bisector of AB. 3. If P is equal to C, sorry, terrible language. Reset. We named our sets. Let's get the point from the set. So let P be any point in S2. Remember, S2 is a set of all of the points that are on the perpendicular bisector of AB. Now I need to prove that P is also in S1. So let P be in S2, I need to show it's in S1. Okay, let P be in S2, and note, if P equals C, comma, then P is in S1. So, if we happen to pick C, I'm saying pick any point on AB's perpendicular bisector, call it P. So pick a point P on AB's perpendicular bisector. You could have picked C. What is C? It's the midpoint of A and B. So it's for sure equidistant from A and B. So we know C is already in S1, for sure. So if you happen to pick C, we already know that's in S1. So now let's handle the case where P isn't C. We need to show that its distance from A and B is equal. Right? So C was just one special case. All right, so we pick P, and what do we know? We know P is on the perpendicular bisector, so I know that this is congruent to this, right? And I know that this is a right angle, and this is a right angle. I am trying to prove that the distance from A to P is equal to the distance from P to B. How can I prove that?
They're isosceles. They're equilateral triangles.
No, we don't know that's equilateral. P could have been right here, P could have been up here, P could have been down here.
We know it's isosceles. Well, not really. No.
We're trying to show that this is an isosceles triangle.
Yeah.
It's a right triangle. We know they're
This one is a right triangle, this one is a right triangle.
Therefore, if there are two right triangles, then it's an isosceles.
No, this angle does not have to be congruent to that angle. We're arguing it is.
And we're arguing.
You guys, all right. Notice that this side is congruent to this side.
Yep.
Oh yeah.
What am I trying to argue? That this side is congruent to this side.
Okay, so side equals side.
Side angle side, we're done. By side angle side, this triangle is congruent to this triangle. So this side is congruent to this side. So AP, the distance from A to P, is equal to the distance from B to P. Okay, so observe that triangle ACP is congruent to triangle BCP by side angle side, which gives me that AP is congruent to BP.
Which means A is congruent.
Which gives me that the distance AP, that distance is equal to the distance BP. Right?
Okay.
And so P, the distance from A to P, is equal to the distance from B to P. That is exactly what we meant when we were saying that P is in S2. What does it mean to be in S2? It means your distance from A is equal to your distance from B.
Yeah.
So we just barely showed if P, S1. We just barely showed if grab a random point in S2, then it's in S1.
Okay.
So every point that's in S2 is in S1. So far we showed that S2 is a subset of S1. We still need to show that S1 is a subset of S2. Because we're trying to show that these two sets are equal. So I showed everything on the perpendicular bisector is equal distance from A and B, but maybe there's other points also equal distance from A and B that aren't on the perpendicular bisector. All I know for sure is if you're on the perpendicular bisector, you're equidistant from A and B. There still could be some other secret points out there that are equidistant from A and B that aren't on the perpendicular bisector. We need to show that that's not the case. So I showed if you're on the perpendicular bisector, you're equidistant from A and B. Now I need to show if you're equidistant from A and B, then you're on the perpendicular bisector. And therefore, those two sets of points are identical. That makes sense? Over-explaining?
No.
Good? Alright, so let's go the other way now. So for this time, let P be in S1. So let's reset our picture here. So we've got our segment AB. We've got our midpoint C. And now we are picking a random point in S1. What's S1? It's all the points who are equidistant from A and B. So pick a random P. This time we'll pick it a little bit different to change our picture. Pick a random P. All I know about P is its distance from A and its distance from B are the same. So I know that is congruent to that. So let P be in S1. And note, if P is equal to C, comma, then P is in S2. Let's handle the C case really quick. You could have picked C as a point equidistant from A and B, but obviously C is also on the perpendicular bisector. So we handled that. So now, whatever P is, it's some point equidistant from A and B, and it's not C. Right? What am I trying to prove?
Trying to prove the distance from A to B is equal from at point C.
No, I know that the distance from A to P and the distance from B to P are equal. I know that. I'm trying to show that P is on the perpendicular bisector of AB.
Okay.
I'm trying to show that if you create this line, PC, if you create that line, then these angles are right angles. That's what I need to prove.
Yeah, well, if it's perpendicular, then it's going to be, that means that AC and CB are equal, right? Because that's what a perpendicular bisector is.
So if P is on the perpendicular bisector, let me show you another picture that right now it could potentially be. Maybe it looks like this. Here's A, here's B, here's our midpoint C. Maybe P is right here. Maybe our picture looks like that. So I need to prove that the line connecting P and C is a bisector. I need to show it's perpendicular. That's what I'm trying to prove.
Yeah.
Okay, so we're good there, right? Now I know C is the midpoint of A and B, so what does that tell me?
AC and CB are equal.
Right, this is congruent to this. Alright, anything else we know?
That the PC is equal to itself.
That PC is equal to itself.
Therefore, by side, side, side.
These two triangles are congruent.
Yeah.
Okay, so I know the triangles are congruent.
Mm-hmm. So if they're congruent, then that means that they have to have the same angles.
Right. These angles have to be the same. Furthermore, we know that adjacent, congruent, supplementary angles have to both be right angles. Make sense?
Makes sense.
Okay, so you've already understood the whole picture. 5. Then, triangle ACP is congruent to triangle BCP by side, side, side. Which gives me that angle PCA and angle PCB are congruent supplementary angles, which gives me that they're right angles. Yes, Kendrick. So they're congruent supplementary angles, which gives me they are right angles. Six. Then that tells me that P must be in S2 because it's on the perpendicular bisector of AB. Right? So then P is in S2. Yes. So that gives me that S1 is a subset of S2. But I already had S2 as a subset of S1. S1 is also a subset of S2, which gives me that S1 is equal to S2, which is what we were after. Make sense?
Makes sense.
So that's a common way that these proofs about locus of points go. You want to show that two different geometric objects, let me say it different. You want to show that one single set of points has two properties. So I was trying to show that the set of points that are the perpendicular bisector of the things are the same thing as the set of points that are equidistant from A and B on the sink. So how did I do that? I let one set be the set of points satisfying the first condition, one set be a set of points satisfying the second condition, and then prove the two sets are equal. Very common proof technique for that. Make sense? Alright, I wanted to do one proof that we fleshed out all the way, all the nitty gritty. We'll rely more on the drawing from here on out. Alright, so next one. The locus of points interior to an angle and equidistant from the sides of the angle is the set of points on the bisector of the angle, excluding the vertex. Okay. So, theorem 13-2 this time. And what's this one saying? This was saying we're starting out with an angle. Here's our angle. First, I want to talk about the set of points that bisect the angle. The bisector of the angle. So the bisector of the angle is the ray that splits this thing in two. So that's one set of points. The other set of points that we're talking about are all the points on the interior of the angle that are equidistant from both the sides of the angle. So here's the sides of the angle. I'm looking for a point that's as far from this side as it is from this side and interior to the angle. Make sense?
Yes.
So would that point work? No. This point is way closer to this side than it is to this side. Does this point work? Yes. This point. Yes. This point. Yes. Yes. And it turns out it's going to be the same set of points.
Yeah. And you're trying to prove that?
That's what we're trying to prove.
Okay.
So I'm going to show that if it's on the angle bisector, then it's equidistant from the sides. And if it's equidistant from the sides, it's on the angle bisector. Okay? So let's go this way first. Which way was that way? 13. We want to show that equidistance from the sides is on the angle bisector. So let P be equal distance from sides. So we've got a point P here, and all we know about P, wherever the point is that it's equidistant from this side and this side. Right? How do we get the distance from a point to a side? We drop down a right angle like that, and whatever the length of that line is the distance.
Yep.
So drop that down to here. We'll say wherever that hits is A. Drop this one up to here. We'll say wherever that one hits is B. But we know that those are perpendicular. And now P, since it's equidistant from the two sides, I know that this has to be congruent to this. Okay. Now what am I trying to show? I'm trying to show that P lies on the angle bisector. I'm trying to show that this angle is congruent to this angle. Because then this is a line that splits the angle perfectly in half. Alright? So how do I argue that this angle is congruent to this angle? I'd get that if I can show that this triangle is congruent to this triangle. How can I argue this triangle is congruent to this triangle?
Well, since the line P is equal to itself on both triangles.
Okay, so I got that this side is congruent to itself.
Yeah.
Good.
And the angle P, well,
Let's name some of these lengths for a second. Let's say that this side has length little a. Then this side also has length little a. And let's say that this hypotenuse here has length little c. What is the length of this side?
it's the,
It is,
oh jeez.
Let's name this side really quick. We'll call it B. I want to figure out what B is in terms of A and C. What do I know about these side lengths? How do they relate to each other?
to get C, it's half A times B.
We're just using the Pythagorean theorem. This is a right triangle, so we can use Pythagorean theorem.
Half A times half.
So I know that A squared plus B squared is equal to C squared. Oh, you're thinking of an area formula.
Oh, okay.
Okay. A squared plus B squared equals C squared. Pythagorean theorem, right?
Yeah.
Yeah.
For this triangle here. Now let's solve for B squared. What does B squared equal?
B squared equals,
C squared minus A squared. So B is equal to the square root of C squared minus A squared, right?
yeah.
That's how long this side is.
B is equal to C minus A, right?
No.
Square root of that, you take.
We'll do this really quick. Notice that 3 squared plus 4 squared is equal to 5 squared.
Okay.
9 plus 16 equals 25.
Okay.
So 4 squared is equal to 5 squared minus 3 squared. 16 is equal to 25 minus 9.
Okay.
I cannot go from that to 4 is equal to 5 minus 3.
How do you have a C squared under a square root? How do you have a square sign under a square root?
Alright, let's continue with concrete example I had up here. So 4 squared is equal to the square root, so 4 is equal to the square root of 5 squared minus 3 squared. Take the square root of both sides. You with me?
Okay.
What's 5 times 5?
25.
Minus 9.
16.
Square root. Gives you 4. So taking the square root of both sides works like that. You can't just get rid of the square root. Otherwise you get 4 equals 2.
Does that work with any number? The square root?
If
No.
I have A is equal to B plus C, it is always and forever the case that if I have A squared is equal to B plus C, then it always and forever is the case that A is equal to the square root of B plus C plus or
No, I'm
minus.
saying if you plug any numbers into that, into 3 squared plus 4 squared equals 5 squared.
Any numbers into this?
No, this is just kind of, if you plug any numbers into that, would it come out?
9 squared plus 10 squared equals 2 squared.
So you're
No,
saying
I'm
plug.
it.
Has to equal.
I don't know what I'm plugging in numbers for. This has all the numbers plugged in.
I'm saying,
This came for plugging numbers
can
into
you
this.
plug in, I know, never mind. It was just off topic.
Only very special numbers will satisfy this equation, and they're called Pythagorean triples. So you can't just plug in whatever you want. I can't plug in 1, 2, and 3.
Okay.
1 squared plus 2 squared is 5. 3 squared is 9. So no, there's only very special numbers that satisfy that relationship. Anyways, so b here, b we calculated was equal to the square root of c squared minus a squared. What is this distance from here to here equal to?
It's b.
It's the same thing. This is also equal to the square root of c squared minus a squared. A hypotenuse squared minus a leg squared. Right?
Yes.
So the distance of this, using the Pythagorean theorem, is the same as the distance of this. Therefore, this side is congruent to this side. And now I get that those triangles are congruent by side, side, side. You see it?
Yeah.
What were we trying to show?
You were trying to show that
What was our initial problem? Reset, reset, reset. What was our initial problem? You're given an angle.
Bisector.
Yep, pick the angle bisector. Here it is. Also, pick all the points inside the angle equidistant from the side. Here they are. We're trying to show that those two things are the same. So I started out with a point P that was equal distance from both the sides.
That was on S1 and S2.
So S1, we can think about S1 as being the point's equidistance. So we'll say S1 is the equal distance. And we'll think about S2 as the angle bisector.
Okay.
Alright, so I started with pointing out S1P.
Yeah.
It was equal distance from both the sides. That meant this segment, let's review out all the logic here. Start to finish. Make sure it's very clear. So I start out with my angle, and I pick a point P, and all I know about P is that it is equidistant from both sides of the angle. Right?
P.
What?
Yes.
So P is equidistant from both sides of the angle. What is the distance from P to this side? How do I get that?
If we know it's equal distance from both sides.
How do I even, if I were to ask you, go get a ruler or a yardstick, and I want you to calculate how far P is from this side, how would you do it? Would you measure the distance from here to here?
No.
From here to here?
Yeah. Yes, and then the
Why
other
not from here to here? Why not from here to here? Why not from here to here? How do you know which point to measure from over here to get the distance to P? It does matter. Imagine I'm trying to see how far you are from this wall. You with me? Should I measure from this point on the wall to you? Or should I measure from this point on the wall to you? Or this point on the wall to you?
Well,
How far are you from the wall?
I guess the closest point to the wall.
So the closest point. Which point is going to be the closest point?
Obviously.
The one that makes a straight angle perpendicular to the wall to you. So I have to measure perfectly perpendicular from the wall to you.
Well,
To
you
get your
can
distance.
go and you can take any point on that line and find an equal distance.
But I want to know how far is P from the line. When I ask how far you are from the wall, imagine this wall goes on forever. And I say, how far are you from the wall? Well, if we use that point over there, then you're 10 trillion miles from the wall. No, you're not. You're 6 feet from the wall. When we talk about the distance from you to the wall, we mean the distance from you and the closest point on the wall. That's what we mean by the distance between you and the wall. Similarly, what do we mean by the distance from P to this side of the line? We mean not the length of this segment.
It's the closest
We mean drop down a perfect perpendicular. We mean the length of this segment. The length of that segment is what we mean by the distance to that side. Similarly, we mean the length of this segment, if that's a perpendicular. That's what we mean by the distance to that side. You with me? Okay, so this is A, this is B. And so far we know that P is equidistant from this side and this side. Or in other words, P is the same distance from A as it is to B. Or in other words, we know that this is congruent to this. What are we trying to prove? We're trying to prove that if we connect P to the origin here, we're trying to prove that this bisects the angle. I'm trying to prove that that is congruent to that. I'm trying to show that if P is equidistant for both sides, then it's on the angle bisector.
Yeah.
Perfect. So we're trying to show that those two angles are congruent. So far, here's the information we have. Now, we also knew that this side was congruent to itself. Right? Perfect. So now I have, this is the right triangle, this is the right triangle. They both have the same hypotenuse. And they both have one of their leg lengths the same. Therefore, using the Pythagorean theorem, this side has to be congruent to this side.
Yeah.
There we go. And now we know that these two triangles are congruent by
Side, side, side.
side, side, side. And since they're congruent, this angle is congruent to this angle.
Okay.
So if it's equidistant, then it's on the angle bisector. All right, now we got to go the other way. Ready for the other way?
Yeah.
So reset, reset. So now we got to go this way. We got to show that if it's in S2, it's in S1. So start the angle. Let's throw in the angle bisector really quick. Here's the angle bisector. And now pick some random point P on the angle bisector. What are we trying to show? We're trying to show that the distance to this line is the same as the distance to this line. Right?
Yes.
So to get this distance, we need to drop a perpendicular. And to get this distance, we need to drop a perpendicular. Call that the point A, call this a point B. And my whole job is to show that this side is congruent to this side. Now I already knew that P was on the angle bisector, so I know that this angle is congruent to this angle. Right? I'm trying to show that this side is congruent to this side.
Yeah.
How do I show that?
I know that P is equal to itself.
The line, the
Let's call this
angle
O
bisector-
so that we can talk about that. There's O.
The angle bisector is
So-
congruent to itself.
We know that this side is congruent to itself. Good.
We're trying to find if A and B are congruent to.
I need to
each
show that this is congruent to this.
other. Okay, so from O to B is congruent from O to A.
We don't know that.
I don't know that
Nope.
P and P is.
We know that. Do we not know that angle OPB is congruent to angle OPA
We do know that. How do we know that?
because of right angles?
Not because of right angles, but because both triangles have the same angle sums. They both have a right angle. They both have that. Therefore, the remainders both have to be the same. Perfect.
Yeah.
And now how do I know that those two triangles are congruent?
Like angle.
Not
Angle side angle.
angle side angle. And so by angle side angle, those are congruent. And so we get this side is congruent to that side. Good. All right. We waking up a little? Getting thinking? All right. Next theorem. Let AB be a given segment, the set of all points P, such that the triangle is right. With that as a hypotenuse, is the circle AB, with that as a diameter. Okay, so for our next one, here's what we're going to prove are the same. Two different sets of points. We start with the segment AB. You with me? We start with the segment AB. First thing we are going to do is we are going to look at all the points who lie on the circle with AB as their diameter. So first thing I'm going to do is I'm going to mark out all the points that would lie on the circle with AB as its diameter. That's S1. So thinking about in terms of S1 and S2, S1 is circle with AB diameter. All right, oops, not S prime, S1. S2 is going to be the set of all points we could choose that make a right triangle with side AB as a hypotenuse.
Okay.
So pick a point. If using that point, when I drop this down, it gives me a right triangle, we include the point. If, pick a point, when we draw the triangle using AB with that point, it doesn't give us a right triangle, we don't include that point. And it turns out all the points that we do include are going to be the circle. So S2 is points P that make triangle APB a right triangle. Or better yet, make APB a right angle. That make angle APB a right angle. Okay. So those are two sets of points that we're trying to show are the same. Right? Okay. So let's start with a point 1 and then go from the other. So let's start by picking P on the circle. So we've got this circle. I pick my point P here. Here's P. I'm trying to prove that APB is a right triangle. How do I do that?
Well, you mirror it.
Huh?
You mirror it.
Well, we've already proven any triangle inscribed in a semicircle is a right triangle.
Okay.
So that's one way we're already done. Or we could have used our theorem from last time. The theorem we ended with last time said that if I inscribe any angle in a circle, pick any angle I want. Here's an angle. Let's pretend that that's the center of the circle. Pick any angle I want. The central angle is twice as big as the circumscribed angle. So if this angle right here were 25 degrees, then this angle right here would be 50 degrees.
Yeah.
You with me?
Yeah.
Now, notice here we have a circumscribed angle. The straight angle here, using the center point, is, how big is this angle?
180 degrees.
So this angle has to be half of that, 90 degrees. So that's another way you could argue it. Another way that we could say this theorem is take any angle inscribed in a circle, the arc length the arc length here is double in degrees. I'm saying the word's weird, but I think you get the idea.
Yeah.
Maybe I said the first time. All right. So that's one way that we could already argue that. Pick P, it's on a circle, then that has to be a right angle. Now we're going the other way. This time, we're going to pick P so that it is a right angle. And now I need to argue it's on the circle. Okay? So I've got A, O. We'll say O is the middle point of those. Really quick. How do I argue that this point also lies on the circle? So I've got A and B here as a segment. I pick P such that it gives me a right triangle. I am trying to argue that P lies on the circle that has AB as its diameter. We've already proven that every single triangle can be inscribed in one and only one circle. That's going back. So there is a circle that goes through it that has O as its origin with AB and captures all those points. And that's it. So that point lies on the circle. Because there's a circle, there's one and only one circle inscribing all three of those points.
Yeah.
And every right triangle can be inscribed in a semicircle.
Okay.
So one and only one circle, it's the one that has to have that as a semicircle, so it's that circle.
You're saying you could put P anywhere on the circle in there?
Here's what I'm saying. Pick any right triangle you want where its hypotenuse is down here. Draw it however you want. But it has to be a right triangle. If what you drew was a right triangle, then this point will be on the circle that has a hypotenuse as its diameter.
I thought you were saying that you could put P anywhere on that circle and you'll have a right triangle.
That was the first way. So that's what we did.
Oh.
So the first way was, here's our diameter. Pick P to be any point on the circle. The resulting triangle will be a right triangle. So if I pick P to be down here, and look at this, this will be a right angle. If I pick P to be right there, and look at that, this will be a right angle. No matter where I pick P on the circle, it'll give me a right triangle. As long as I don't actually pick a point A and B, obviously, because then we don't have 3 points. Good?
Yeah.
All right, next theorem. Theorem 13-4. The bisectors of the angles of a triangle intersect at one point called the incenter, which is equidistant from the three sides. Okay. So this time, we're looking at a triangle, some random triangle, doesn't matter what it is. And now we're going to look at its, which ones were we doing? All its angle bisectors. So I'm going to bisect each one of the angles. So I try and bisect this angle. Try and bisect this angle. And try and bisect this angle. I'm trying to prove, one, all those angle bisectors intersect at a single point. That's one thing I'm trying to prove. And number two, I'm trying to prove, and the distance at this point is from this side is the same as the distance this point is from this side, is the same as the distance this point is from this side. Make sense?
Yes.
Okay, so let's get started with this proof. So first off, start with our random triangle. And I'm going to draw two of its angle bisectors. There's one angle bisector. I don't know how well you can see that. And then we'll draw another angle bisector. We'll pick this one. Okay. Now, the two angle bisectors for sure intersect at a single point.
Yeah.
Maybe start labeling some of these points. A, B, C. The two angle bisectors for sure intersect at a single point. We already know that. What we need to show is that if I connect this point O, if I connect point O with B, then it will also bisect this angle.
Okay.
That's one thing I need to do. The other thing I need to do is I need to show that if you drop the altitudes here, then they're all equal. So if I drop this down, so this comes down at a right angle, then that's the same as if I drop this one down. And that's the same as if I were to drop this one down. So I need to show all those distances are the same.
You're saying, so that would be the midpoint of the triangle?
Not the midpoint of the triangle. We've already defined the middle of the triangle. What's the middle of a triangle if I have some triangle? Draw the circle that inscribes all those points, and it's the center of that circle. So notice that sometimes the center of a triangle isn't even inside the circle. Actually, that might have just been for regular polygons. We'll have what we call, this is called the incenter, and then we'll have another point. We'll get to it later. But for now, this point's called the incenter. Okay. Let's see. So, I'm not sure which way I want to go first. I think I just want to, let's see what we know here. I know that this angle is congruent to this angle. I know that this angle is congruent to this angle. And if I connect this, I'm trying to show that this angle is congruent to this angle. How am I going to do this?
Well, if you've already, have you already proved that if you connect, is that your angle bisector?
So I know this is an angle bisector. I know this is an angle bisector.
You're trying to
They
prove
intersect at a point O.
if
I'm trying to argue that OB
is an angle bisector.
is an angle bisector.
And if so, then the angles would be congruent.
So let's get rid of going all the way through. So I'm going to draw the angle bisectors just to this point because I think it'll clean up my picture. So here's the angle bisector from here, going to that point, stopping. Here's the angle bisector from here, going to that point, stopping. And then I connected this point to here. I don't know if this is an angle bisector. That's what I'm trying to prove. Okay. Another thing I'm going to do is I'm going to drop 3 verticals down. Okay, yeah, I already like this plan better. So drop a right angle down like that. Drop a right angle down like that.
And these
And
aren't,
drop a right angle down like that.
and these aren't part of A, B, and C's lines.
No, they are not a continuation of the line. So let me do the bisectors in blue. So blue are the angle bisectors, and black is dropping down perpendiculars.
Okay.
Okay. Now, what do I know about the points on an angle bisector inside of an angle? Going back to one of our previous theorems. If I know that this point lies on the angle bisector, I know its distance from the sides has to be congruent. Right? That's a theorem we already did.
Yeah.
All the points on an angle's bisector are equidistant from both sides of the angle. Right?
Yeah.
Okay.
You gotta prove that those are congruent to each other.
So I know that this is congruent to this. Because here's the angle bisector of this angle. Here's a point on its angle bisector. Therefore, it's equidistant from both these sides. So I know that this side is congruent to this side. Similarly, it's on this angle bisector, so it's equidistant from both these sides. So I know that this side, this angle, that side is congruent to this side.
Okay. And B's bisector is congruent to itself.
And then this bisector right here is congruent to itself. These are both right triangles using Pythagorean theorem. This side is congruent to this side.
So through theorem side, 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 B.
That angle is congruent to that angle. And so it's a bisector. So that point, so all our bisectors intersect at one point, and that one point is equidistant from all the sides. And that's called the incenter of the triangle. Make sense?
Yeah.
Okay, that one was cool. Got stuck for a sec, but figured it out. That was theorem 13.4. Moving on to theorem 13.5. The perpendicular bisectors of the sides of a triangle intersect at one point, called the circumcenter, which is equidistant from the 3 vertices. Okay, so let's see if we can figure this one out. So we've got some triangle now. Call the points A, B, C. I am trying to show that all the perpendicular bisectors intersect at a single point. So perpendicular bisector is split this side in half, pick the point. We'll call that one E, I guess. And I guess we'll use this side as well. We'll call that one F. Construct their perpendicular bisectors. Let it come out however far it comes out. This one comes up however it comes up. So those two perpendicular bisectors for sure intersect at one point. Pick G on this side. And what are we trying to show? We're trying to show that this line, maybe where these all intersect, we'll call it, I have to draw a line over there, we'll call it O. We're trying to show that OG is in fact perpendicular. So all our perpendicular bisectors intersect at a single point. And then we also need to show that the distance from A to O is equal to the distance from B to O is equal to the distance from C to O. All right. So how are we going to start this? What do we know about all our different side lengths here?
They're all equal to their other side.
Yeah, they're all equal to their other side. So I know that this side is congruent to this side. I know that this side is congruent to this side. And I know that this side is congruent to this side. I'm trying to argue that this and this are right angles. If I get that these two triangles are congruent to each other, then those two have to be right angles. So we need to get that this triangle is congruent to this triangle. That's big picture where we want to get. Somewhere along there, we also need to capture the fact that AO is the same as BO is the same as CO. Right? So we're right there so far.
Yeah.
You see any relationship between these two triangles?
A is congruent to itself. A to O is congruent to itself.
Or, sorry, these two triangles?
Oh, yeah, they're
E is congruent
basically
to
the
itself.
same. And so EO is congruent to itself.
So this side is congruent to itself. So what do I know about this triangle and this triangle?
They're equal.
They're congruent. They're congruent by side, angle, side. Side, angle, side, right? So that gives me that this one's long side, I'll put a V on it, is congruent to this one's long side. Right?
Yeah.
Now similarly, this triangle is congruent to this triangle by side, or by side, angle, side. Side, angle, side, right? And so this side's also congruent to this side. We'll put a V on it. So that side's congruent to that side's congruent to that side. Okay, so we got that this point O is equidistant from all three vertices, right? What remains to show is that this angle and this angle are right angles. Right?
Yeah.
How can I show that these two are right angles? I need to show that they're congruent. How do I know that this angle is congruent to this angle?
Because O and OG is to itself, so by side, side.
By side, that triangle is congruent to that triangle. Perfect. And so this is, in fact, a right angle. And so O lies on the perpendicular bisector from G as well.
Yeah.
So there we go. We got all three perpendicular bisectors intersect at a single point O. Furthermore, that point O is equidistant from the three vertices, which is what we were after. So where all the angle bisectors intersected was called the incenter. And make sure I don't say any of this wrong. I think it's called the circumcenter. But yes, and where all these intersect is called the circumcenter. Why is it called the circumcenter?
Because it's where all the points meet.
It's called the circumcenter because it's the center of the circumscribing circle. Take the circle that goes through A, C, and B. Whatever that circle looks like. I'm going to butcher it, but we'll just throw it up here. Just try. Take the circle. Okay. That was awful. Take the circle that goes through A, B, and P. Notice that the distance from A to O is the same as the distance from B to O is the same as the distance from C to O. It's the radius. So that would be the center of the circumscribing circle. Make sense? Okay. Last one. The medians of a triangle intersect in one point called the centroid, which is 2/3 the distance from each vertex to the midpoint of the opposite side. Okay, so let's do this last one. What's the median?
The median is the middle. It's
The medians of a triangle intersect in a point called the centroid. So let's get our triangle up here. So how do we get, let's really quick label A, B, C. So by medians, what do we mean? We mean pick the midpoint of each of these lines. So the midpoint here, we'll call it E. The midpoint here, we'll call it F. And the midpoint here, we'll call it G. A median is a line that connects a vertex to the middle of the opposite side. So here's a median. And here's a median. And our last median would come down through here. But that's our median point. My picture is lined a lot. I didn't draw it very well. So G right there. So what are we trying to prove? We're trying to prove that these three medians all intersect at one point. That's one. The next thing we're trying to prove is that whatever this distance is, call this distance x, this distance is 2x. And call this distance, if this distance is y, this distance is 2y. And if this distance right here is z, then this distance over here is 2z. That's what we're trying to prove. Those two things. All intersect at one point, and all these lines are cut on a 1/3, 2/3 ratio. 1:2 ratio. Make sense?
Yeah.
Okay, so that's what we're trying to prove. Let's reset and start out our picture and see how we can figure this out. Maybe I'll try and just be a little bit more accurate with this one, so it seems like just by eyeballing it, my picture wasn't turning out all that great. Oops. Yeah, good enough. So, draw a triangle up here really quick. Try and keep lines as close to straight so that it doesn't look awful. We can clean up. That back. Okay. So we got A, B, C, and really quick, give two middle points. So let's see, going from there to there, that was 11 inches, cut in half would be roughly 5.5. So there's the midpoint, and we'll calculate midpoint out here. That is about 17. What's half of 17? 8.5. So about right there. Okay. And now I'm going to draw in two median lines. And we'll go from there. So one median line goes roughly like that, and one median line goes roughly like that. Okay.
Bisectors, right?
Not bisectors, no, medians. Medians. So what does that mean?
Oh, from the middle of the line.
Perfect. So A, B, C, call that D, call that E. So what that means is that this segment is congruent to this segment, and this segment is congruent to this segment.
What are you trying to prove?
So if we were to construct the median now from B, we need to prove it goes through that point. That's one thing we need to show. The other thing that we need to show is that the distance, let's really quick label that median, that middle point. We'll call it O. I need to show that the distance from E to O is half the distance from O to A, and the distance from D to O is half the distance from O to C. Okay. I think I'm going to prove the ratios first and then worry about crossing this through after. You with me? So, I'm going to start by looking at this triangle. So I'll put that line in and look at triangle BDE and see how that compares with triangle BAC. They're similar because this bisects each of the halves. So I know that this angle is congruent to this angle, and I know that this angle is congruent to this angle. Oops, this angle and that angle, right?
Yeah.
Furthermore, if I say that this side right here has a distance of little a, what's the distance of this?
Little a squared.
Big A.
2 little a. It's twice as big. This triangle, because it has to maintain the ratios, since this is half the distance of this, and since this is a half the distance of this has to be half the distance of that. That's what it means to be similar. All those proportionalities are preserved. You with me?
Yeah.
Okay, so now, kind of erasing those angles, we got the information we need, I think, from that. The fact that if this side is little a, then this side is 2 little a. Because I think now I'm going to want to look at this triangle, DOE, compared to this triangle, OAC. Maybe one more thing we should have pointed out. What do I know is the relationship between this line and this line? How does this line compare with this line?
It's
They're parallel.
They're parallel. You're right in the length of the segment, but what I was going for is the fact that they're parallel. Let me try and do that one more time a little bit better. Wow, that was awful.
That was worse. Okay.
It was much worse. One of these days, I'm going to have to reteach this whole class using just online tools. Alright, that's a little better. Okay, so I know that this line is parallel to this line. Okay, so now, how does this angle compare with this angle? This angle has to be congruent with this angle. They're opposite interior angles for 2 parallel lines. The way you were used to seeing that is you have a parallel line, and a transversal. And so this angle is congruent to this angle, and this angle is congruent to this angle, called opposite interiors. So I got 2 parallels, and here's their transversal. So I know that angle is the same as that angle. Similarly, I've got 2 parallel lines, and here's a transversal, which gives me that this angle is congruent to this angle. With me there? Now I need to argue those 2 triangles are similar. If 2 triangles have 2 angles in common, then they're similar. So this triangle is similar to this triangle. The way you can see it, if you're still not getting it, is notice that these are vertical angles. Vertical angle, vertical angle. Right? So now, I know that this triangle is similar to this triangle. Good? What do we know about similar triangles? They're proportional to one another. So if this side is half the length of this side, then this side, the one using the 2 angle, has to be half the length of this side using the 2 angle. So if this right here is little b, then this is 2 little b. Similarly, if this side right here is little c, then this side right here has to be 2 little c.
Oh, God.
Okay.
Yeah.
So now what we got is that point cuts the line exactly into a ratio of 1 to 2 and 1 to 2. You with me? Now we still have one more piece of our proof that we need to do. So, drawing now our picture, trying to draw roughly the same triangle. I'm going to do this one a lot more fast and loose. So we had that point O, which we know was the intersection of the median going this way and the median going this way. Then we had that point O, right? We were trying to argue that it also lied on the median going this way. That's what we were trying to argue. How would we argue that? Well, we would redo the same proof. Just get rid of this line for a second. And just do the same proof again using these 2 median lines. What would I have discovered? I would have discovered that if we called this one here C, or D, if we would call this distance little d, this would have been at 2 little d. And if we would have cut this one right here, this would have still been the same 2b and b, right? And so, since this goes through that point, and this goes through that same point, there's only one point on this line. There's only one point on this line that splits it exactly into a ratio of 1 to 2. And so this transversal, or sorry, not this transversal, this median line goes through that point, and this median line goes through that point. So it's like redo the same proof again, just using a different transversal. Since they both cut this using a different median, since they both cut this median at the same point, they have to be the same point. Does that make sense?
Yes.
Okay. Now I said that was the last proof, but I lied. We have one more proof now. Our next proof is to prove that the altitudes of a triangle intersect in one point. What are the altitudes of a triangle?
I don't know.
The altitude is what you get when you drop a right angle. So if I have this triangle, one of its altitudes is this.
It's height, right?
Gives you the height. If I think about this as a base. If I thought about this as a base, then this would have been its altitude to give me a height. And if I would have thought about this as its base, then this would have been the altitude to give me its height. And so the 3 altitudes intersect at one point is what I'm trying to prove. You with me?
Yeah.
Okay, how am I going to prove this? I'm going to start out with my triangle. And now I'm going to do something really weird. I am going to, so here's my starting triangle. You're going to lose my starting triangle as I draw this picture, I think. So let me try and be a little bit careful. I'm going to, through A, draw a line parallel to BC. So, I don't know, does that look roughly parallel to BC?
Roughly.
So we'll draw that line, trying to be parallel to BC. I'm going to draw a line through B, and I'm trying to make it parallel to AC here. That's my intent. And then I'm going to go through C and try and draw a line parallel to AB. At least that's my intent. And it gives me this new resulting triangle. Hopefully you see it. With the points E, F, G. D, E, F. Makes more sense. I was wondering why I skipped E. Okay. Now, since they're parallel, since I kept everything parallel to what it roughly looks like it's parallel to, what did that give me? It's going to give me a whole bunch of angle congruences here, but let's start drawing a bunch of them in. Since this line is parallel to this line, then this angle is congruent to this angle, and this angle is congruent to this angle. You see that? And now, we'll just call this angle right here angle 3. 1, 2, 3. Okay, looking at the fact that these two, well, how's the easiest way to quickly see this? Yeah, I guess we can say it that way. So, looking at the fact that these two are parallel, that gives me that these are opposite interior angles. So this one right here has to be a 3. Now, since that's a 1 and that's a 3, this one has to be a 2. And then looking at these two as parallel, then that gives me that this is a 1. And if that's a 1, then this one right here has to be a 3. And then if that's a 3, this one has to be a 2. No, this one has to be a 1, I mean. Because 2, 3, and 1 gives us a straight angle. So that's a 1. Over here, this has a 1 and a 3, so it has to have a 2. Over here, this one has a 1 and a 2, so it has to have a 3. And so we see, all those triangles are similar triangles. Furthermore, they share sides, share sides, share sides. And so by side angle side on each of these, we get that all these triangles are congruent to each other. You see that? So I know that this is congruent to that, this is congruent to that, this is congruent to that.
And they're all equilateral triangles.
Not equilateral, no, just all congruent to each other. And all similar to each other, and it turns out they're all congruent to each other. Each of these 4 triangles. Because this is side length 3. This is the same big as that side. This side over here is going to be side length 1. And this side is going to be side length 2. So this one's like a flipped over version of these ones. These ones are all oriented the same. That one's flipped over version. Now remember what we were trying to show. We were trying to show that the altitudes of this triangle all intersect at one point. But now notice that the altitudes of this triangle are just the perpendicular bisectors of this bigger triangle. An altitude through this point is just a perpendicular bisector of this side. However it goes through. I don't know where it goes through. We'll just stop drawing it once we get to there. But it's a perpendicular bisector of this side. Furthermore, an altitude of that is just a perpendicular bisector of this side. And an altitude of from here is just a perpendicular bisector of this side. We've already shown that all the perpendicular bisectors of a triangle intersect at one point. So all the altitudes of this triangle intersect at one point. Because all the altitudes of this triangle are the perpendicular bisectors of this triangle. So they intersect at one point. And so that's the last one, and it was just drawing that bigger triangle and then using something that we'd already proven. Okay, so that is the end of chapter 3,
13.
chapter 13. Next week we will move into, well, I guess we got test next week, right? Or review, then test, so maybe over 2 weeks. And then we'll get into 3-dimensional spatial geometry. So that's what we have to look forward to.